Hello everybody, this is Mr. Mac. This is our first video presentation of Unit 2. I'm hoping to get to the point where we can cover all of Module 9 and 10 today. So, as always, if you have any questions, feel free to send me an email or chat with me in class. So, let's go ahead and get started. Unit 2 basically approaches the biological basis of behaviors. The first part, we're dividing Unit 2 into two parts. The first part will contain modules 9 through 15. We'll be taking a close look at neurotransmission and biological psychology, how psychology affects our biology and vice versa. We're also going to take a long, hard look at the various lobes and hemispheres of the brain, and as well as the primal brain, or what we call the older brain, which is the brain stem and some of its surrounding elements. We also will be taking a look at the cerebral cortex, the wrapping paper, in essence, that goes around our brain. And like I said, the hemisphere and how they're organized and how it helps handle our consciousness as far as we know. And then we'll look at genetics and how they impact our individual differences from one person to the next. And then also taking a little bit deeper look at evolution and how it applies to human nature. All right, so that's kind of an overview of 9. Let's go ahead and get started. So again, like I said, Unit 9 is going to be modules 9 through 15. This is 9 through 15 in your textbook. That aligns with Unit 3. And then the second part will align with Unit 5 in the textbook. Again, that's the old framework that aligns with 3 and 5 in your textbook. The new framework calls that Unit 2. Okay, just keep that in mind. Okay, so for Unit 9, at the end of this unit, we all should be able to explain why psychologists are concerned with biology, because there is a direct link, and we'll take a look at that. 9.2 and 9.3 and 9.4 is all about looking at the neuron and neurotransmission. You will need to know the pieces and parts of the neuron, how neurotransmission works, and how neurons work together in a chain, and how neurons themselves communicate through electrical and chemical impulses and release. Okay, so real quickly, one of the people that we need to chat about is a guy by the name of Francis Gall. Francis Gall starts a science back in the 19th century called phrenology, and phrenology is basically the study of lumps on the head. And those lumps, according to Gall, were responsible for different regions, or it's kind of like a roadmap that could tell you where different parts of the brain were. And in the case of Francis Gall, he believed that the mind was assigned to different parts of the brain, or different regions of the brain. So I'm going to show you real quickly a picture of Francis Gall's phrenological map. Phrenology is spelled P-H-R-E-N-O-L-O-G-Y. Phrenology. Again, his name is Francis Gall. And that image is right here. So if you could just hold tight 1 second. Okay, so let's take a look at this image. I'm having a hard time loading that image from Francis Gall. We'll talk about Francis Gall in class. But as you can see here, this is an image of how science best understands the mind today. And you can see all sorts of different areas of the brain, from arousal to coordination to recognition, memory, emotion, smell, etc., etc., etc. And one of the things that psychologists look at is how each one of those parts are divided up among our consciousness. And that simply means that how do all of these pieces and parts that make up the physical aspect of our brain, how are they connected with all of our behaviors and our senses? Okay. All right. So let's talk neuron. You all need to know what a neuron is. You need to know the parts of a neuron. This image here is an actual picture of a human neuron. I have a video that we'll look at in class that can actually show us the inner workings of a neuron and a neuron as it fires. You do need to know all of these different pieces and parts of the neuron, folks. You will have part of your test that will ask you specifically, what is this? This is the cell body, also called the soma, S-O-M-A. The dendrites, these are basically like little fingers that extend out and help support cell bodies to other cell bodies. All right, this is the cell itself right here in the middle. This long, narrow passageway is called the axon. All right, that axon is further covered by a fatty substance called the myelin sheath. Now, most neurons have this myelin sheath, not all, but this myelin sheath helps the conductivity of the electrical charge that gets sent from the cell body down to the end of the axon. At the end of the axon, we have what's known as terminal branches. Those terminal branches, also sometimes they're referred to as terminal buttons or axon branches. These little tiny bits at the very, very tip, they look like little suction cups. These are your synapses. Okay, these are where your synapses are located, and these are called terminal or axon buttons. Both terms are correct. The last thing you need to make sure that you have an understanding of is the neural impulse. This is an electrical charge that is sent down the axon through the terminal branches down into the axon or terminal buttons into the next cell. Okay, and it's much like a chain link fence. That electrical signal then gets sent from one part or one neuron to the next neuron to the next neuron to the next neuron, and this all happens within thousandths of a second. Okay, right here, this is what keeps the cell alive. This is called the cell body or the soma, like I said, S-O-M-A. Make sure you understand that. This is what keeps the entire neuron alive. All right, let's take a look at the dendrites. The dendrites are basically receive and handle incoming messages from other neurons, and those neurons can come in and attach with their axon buttons and attach here, or they can attach to the dendrites themselves. All right, basically their job is to secure the axon or the neuron, and also to relay that electrical / chemical message from one neuron into this neuron. Okay, and we'll take a look at that when we look at the synapse. Okay, so the axon. What is the axon? Again, think of this as like an electrical wire that carries electricity, and that's pretty much what it does. It's a little more complicated than just that, but we'll talk more about that later. The myelin sheath is next. Basically, this is what we would consider an insulator, and it wraps the conductive axon, and basically this prevents shorting. If you've ever been electrocuted and you've accidentally touched a live wire, you know what that feels like. Most wires should have an insulating covering on them, and the axon is very similar to that. The axon needs an insulating cover so it doesn't short out or shock something near it. It also helps with transmission speed as well as insulation. Okay, so why is it so important? So a lot of babies at birth, they don't have a fully myelinated axon. And a lot of times this continues to develop and grow through 25 years of age. And we think that there's something to do with the fact that the myelin sheath is related to, or the thickness of the myelin sheath, or the quantity of the myelin sheath is related to how much we are able to learn. And then by the time we age and get to about age 25, our ability to learn becomes slightly less. And a lot of that we think is due to our ability to mature and to grow and to take in new experience. And as we age, when you have deterioration in the myelin sheath, you end up with neurological impairments like multiple sclerosis. Okay, so terminal branches. These are the ends of the axons, and these contain terminal buttons, or sometimes called axon buttons, and they hold synaptic vesicles. A vesicle, think of it like a very, very small purse that contains, in this case, small little neurotransmitters, and we'll talk about that in just a second. Make sure that you complete your artwork project that is due in this unit, in these first two modules. You need to make sure you have all of these pieces and parts drawn onto the neuron, and make sure you know where they're located. There is a beginning of the neuron and there is an end. Okay, moving on. Glial cells. Glial cells. All right. So glial cells are kind of like, they're like the support cells. They help the neuron grow. They help the neuron take care of itself. All right. They provide nutrients. They help with insulation in the myelin sheath. They help position neurons so that they can attach to one another, and any kind of excess ionized particles or neurotransmitters that might fall out of the what we call the synaptic gap, which we'll talk about in a second, they would be responsible for general upkeep and cleaning up those neurons and neurotransmitters. Okay, so this is where it gets a little confusing. You need to make sure you understand how neurons generate what we call an action potential. So what this is called the minimum threshold. All right, the minimum threshold is the amount of chemical imbalance caused by ions, and we'll talk about that in a second. But it causes, that imbalance gets to a point, and once it hits a certain level, which is that threshold, then the axon will fire, releasing an electrical surge from the cell body down through the axon towards the dendrites and the terminal buttons. All right, this is what is referred to as the action potential. That is the electrical charge as soon as it fires from the cell body to the dendrites. Okay. All right, so what is a threshold? So if we look at it this way, all right, and what happens is these axons are going to allow, they're actually what we call permeable or semi-permeable, which means they can actually open holes in the sides of the axon and take in or push out sodium and potassium molecules. Sodium and potassium molecules will carry a positive or negative charge. And basically the way these neurons work is they will start to pull in either a bunch of negative or a bunch of positively charged ions to create either a negative or positive charge within the axon. And what happens is, think of it like filling up a bottle that's balancing on top of a pencil. Okay, it's easier to balance an empty bottle, but as you start to fill that bottle, all right, that threshold is building. Once you get to a point, the weight of that bottle will cause whatever it's setting on. A pencil is probably not a great analogy, but once it gets to a certain weight, that bottle is going to want to tip over. Okay, and when that tips, that would be symbolic of the axon reaching its what we call action potential and breaking that threshold and firing. Okay, and then after it fires one time, it sends an electrical charge down through the axon, down into the dendrites once it hits the action potential. All right, and then it comes back down into what we call the resting potential. This is where it recharges. Okay, so all or none response. This is in regards to that threshold. Think of it as a gun. When you pull the trigger, you can put a little bit of pressure on a trigger. For those who've ever fired a weapon, a gun, a crossbow, BB gun, whatever, you can put a little bit of pressure on that trigger and it won't fire, but you get to a certain amount of weight, poundage usually, like pounds per square inch, and then that trigger will release. Okay, that is an all or none response. It's either going to fire or it's not. Okay, and that is exactly what we have here in the case of a neuron. Okay, so now, neural impulses can either be excitatory or inhibitory. All right, so what we mean by excitatory, this is basically like pressing the gas pedal in a car. All right, when we hit the gas pedal, it goes fast. This is excitatory, meaning that an excitatory neurotransmitter triggers an action. All right. Think of it, it's similar to our fight or flight reflexes. Okay. Um, if we are excited about something, what's going to happen is our body's going to release adrenaline and our heart starts beating really fast, our blood pressure goes up, our vision narrows, time almost seems to slow. All right. Inhibitory signals, on the other hand, these are the signals that are like hitting the brake pedal on a car. All right. They're inhibiting whatever action is going on. So in this case, neurotransmitters that are inhibitory actually will slow or depress the action of previous neurotransmission. All right. So again, if you can just equate this to either the gas pedal being pressed under excitatory or inhibitory, pressing the brake pedal, increasing the speed, decreasing the speed. Hopefully that will help keep things clear in your mind when we're talking about neural impulses being excitatory or inhibitory. Okay, next, resting state of an axon. All right, so before we begin the action potential, all right, before we begin the action potential, let's go back there real quick. You can see this right here. We are at a resting stage. All right, once we go through the firing process, we're building the charge, we break the threshold, and that means we're firing, and this is the maximum at which that neuron will fire, which is the action potential, and then it will fall back down underneath that threshold. It'll actually drop down just a little bit, and then come back to a resting potential. Okay, so let's go back. Okay, so what this means is, prior to the action potential starting to spike, all right, there is the axon's membrane actually will allow positively charged sodium ions. And what's happened is that after that action potential has fired, those ions inside of the axon have gone from being positively charged right before the point of the firing of that axon now to a negative charge. In class, I'm going to show you this a little bit more in depth. So this is kind of confusing, but if you think of it like garden or like water in a garden hose, as soon as you turn that spigot on, all right, what happens? You have a bunch of water that pushes out the end of that hose. Okay, that is similar to a neuron crossing the threshold and firing up to its action potential. And then when you turn that hose off, what happens? Well, that water ceases to push out of that hose and is then replaced with air. So if you think of a garden hose, when we're talking about an axon in a resting state, think of the air being negatively charged ions and think of water being positively charged ions. Okay? So basically, when these positive ions of sodium and potassium, sodium is Na, potassium is K, when these axons become when they fire, there's nothing left. All right, think of the ions being left in the axon as air in a hose. All right, they're negatively charged. They do not carry a positive charge. So what will happen is that axons will then open small little holes in their sides, and they'll push out the negatively charged ions and pull in positively charged ions, thus working to build their action potential. All right, it's kind of like reloading a gun. All right, okay, so again, this creates a slightly negative charge, and the neuron is said to be at the resting state or polarized. Okay, all right, so again, how does this happen? I talked about selective permeability. They can allow, or they can push in or push out positively or negatively charged ions. All right. When ions are being exchanged, this is called depolarization. All right. Depolarization. Now, when these permeable holes are closed, that is called polarization. All right, what we're doing is when we're creating a polarized condition, we're preventing ion exchange. All right, let's take a closer look at that. Okay, in this case, the first section of semi-permeable holes in the axon will open its gates. All right, once the threshold is met, Basically, we have met that minimum threshold and we're starting our action potential. This is basically equivalent to us turning the water on, allowing water to pass down the garden hose. The negative would be symbolic of the air in the hose. The positive would be symbolic of the actual water molecules in the hose, okay? So what happens is sodium ions, positively charged, flood into these holes, and think of it as a ripple effect. All right, so what happens is those holes will begin opening here and they will begin to push, thus creating an electrical charge. All right, and it will travel from the soma, or the cell body, all the way down to the dendrites. All right, so what about a sodium? All right, why do the sodium ions rush in? All right, so the sodium ions are trying to balance out the charge. All right, so they rush in because what we have is an imbalance here, folks. And in this case, it's like kind of like holding a bag under water that's full of air, okay? And if you pop that bag, there's pressure wanting to get in. All right, so if you maybe you stick a pencil in it, or you keep this bag under water that's full of air, what's going to happen? You pop that bag and the water is going to push to get in. Well, these sodium ions are very similar to that, okay? They're trying to create balance, all right? And they do that by flooding into these gates, all right? This is called depolarization. All right, the next step after depolarization is basically we're going to see those negative potassium, or I'm sorry, positive potassium ions will be pushed out through the membrane as the positive sodium are pulled in. All right, again, think of this as air, water, and air. All right, we're creating an imbalance here, and that imbalance will actually cause the firing of the axon. Okay. All right. So, whoops, went too fast. How do the potassium ions move out? So basically the way it works is as the sodium floods in, the potassium gets pushed out. Okay, again, you're creating like a ripple effect. All right, this is called repolarization. So we have to go through a depolarization after firing, and then we go through a repolarization. So that depolarization that happens first, we are getting rid of any kind of those positively charged ions. We're creating an imbalance. All right, so when we repolarize, we're opening those gates to try to balance everything out. All right, so the sodium and the potassium pump continues to depolarize new sections of the axon and repolarize the previous. So basically, guys, like I said, this is a chain reaction. It starts on the left side. If we just consider the left side to be the beginning of the cell body or the soma, it's going to push down towards the axon, down the axon towards the dendrites and the terminal buttons. Okay? And that's pretty much what I just said. It is very much like a series of dominoes. All of this is happening within fractions of a second. Okay? Okay. We will pick up with refractory period in the next segment, so hang tight, and I'll be right back with you.